Two streams of refrigerant 134A are mixed in a mixing chamber. One stream enters at 1 megapascal and 20 degrees C. The other enters at 1 megapascal and 80 degrees C. If the warmer stream has a mass flow rate that is 1/2 that of the cooler stream, determine the temperature and quality if it is a two-phase mixture at the exit. We'll begin this problem with an appropriate illustration. First, let's note that we have a mixing chamber, so we have two flow streams that come together into one. Let's just let 1 and 2 represent the two inlet streams and 3 represent the exit stream. Now we're given in this particular problem the thermodynamic state of each of the two inlet streams. So P1 is 1 megapascal and T1 is 20 degrees Celsius. Further, P2 is the same 1 megapascal and T2 is 80 degrees Celsius. I might also note that since the pressures of each of the two inlet streams are the same, then the exit stream has to be the same as well. So P3 is actually known. It's the same as P1 and P2, which is the same 1 megapascal. Now further, we're told that the warmer stream has a mass flow that's half that of the cooler stream. So m dot 2 is 1/2 of m dot 1, so that's known to us. And what we're trying to find then is the temperature at the exit and, if appropriate, the quality at the exit. We don't know if it's a two-phase mixture or not. We'll see. So this is our problem statement as it's illustrated. Now, this is clearly a first law problem. It's a multiple stream steady flow process. It's not single stream. So for a steady flow process for multiple streams, the first law is simply Q dot minus W dot equals the sum over all exit streams of m dot E times the enthalpy at the exit plus the kinetic energy and the potential energy at the exit, and then minus the sum over all inlet streams of m dot I times the enthalpy at the inlet, and then plus the kinetic energy and potential energy at the inlet. Now, several of these terms can be neglected. First, we know nothing about the heat transfer for this problem. Typically, mixing chambers would be well insulated because we're not desiring to lose heat into the surroundings or gain heat from the surroundings. We're simply trying to mix the streams together. So, given any lack of information, we really have no choice but to assume there's no heat transfer. Additionally, there's no mechanical work devices, like mechanical mixers or anything, so the W dot term goes away. And further, we have no information about the geometry of the problem. We don't know the pipe diameters or areas. We don't know anything about the velocities. We know nothing about the height change. We just don't have that information. So we really have no choice but to neglect both the kinetic energy terms as well as the potential energy terms. So this greatly simplifies our first law. We get then that 0 equals the sum of the exit streams of m dot EHE. There's only one exit stream, so that's just M3H3. And then minus the sum over all inlet streams of m dot IHI. So we've got two inlet streams, m dot 1H1 plus m dot 2H2. Now, this is our first law, but it can still be simplified. Let's keep in mind that we need to use the continuity equation, which tells us that masses conserve. So the sum of the mass flow at the two inlet streams, m dot 1 plus m dot 2, has to equal the mass flow rate at the exit stream, in other words, m dot 3. And then furthermore, we know that m dot 2 is 1/2 of m dot 1, so we'll just rewrite this as m dot 1 plus 1/2 m dot 1 equals m dot 3. In other words, m dot 3 is going to equal 1.5 times m dot 1. Now, this equation is going to be plugged in above into the first law. And additionally, the fact that m dot 2 equals 1/2 m dot 1 is also going to be plugged into the first law. So let's plug these terms in. So our first law becomes the following. So we have 0 equals, now instead of m dot 3, we have 1.5 times m dot 1. So 1.5 m dot 1 h3, and then minus m dot 1 h1, and then plus 1/2 m dot 1 h2. Now if we divide out the m dot 1, those terms go away. We can now solve this for h3, and then going through the mathematics, we get h3 equals h1 plus h2 over 2 divided by 1.5, or 2h1 plus h2 over 3. Now if we look at this equation, we should see that the problem is now solved. We know the enthalpy at 3 because we have h1 and h2, knowing state 1 and state 2. We also know P3. Knowing P3 and H3, we should be able to go into our property tables and find the temperature and the quality as applicable. So now let's finish up the problem. Let's get our thermodynamic property data. So first let's look at P1 and T1. Now we might notice here that pressure and temperature are independent and intensive properties, so we certainly know the thermodynamic state. However, we don't know yet whether it's compressed liquid, superheated. However, if we go into our pressure property table, and that would be table A12, and look up the saturation temperature, what we're going to find is that the saturation temperature at 1 megapascal is actually greater than the given temperature. So this tells us that it's a compressed liquid. So when we have a compressed liquid, our only choice is, since we don't have good compressed liquid tables in our textbook, is to just assume that the enthalpy is approximately the same as the enthalpy of the saturated liquid at the same temperature. So this is actually something that we're going to have to look up in table A11. And at the given 20 degrees Celsius, we'll see that the enthalpy is 79.32. So 79.32 kilojoules per kilogram is the enthalpy at 1. Now at P2 and T2, we'll go back into table A12, and here we see that this is superheated vapor. At the given pressure, we have a temperature that is now greater than the saturation temperature, so this tells me it's superheated. As such, we're going to get H2 from table A13. So from table A13, we go into the 1 megapascal subtable, read down to the 80 degrees Celsius line, and we get that the enthalpy is equal to 314.27 kilojoules per kilogram. So now we have H1 and H2. We simply plug these in above, and we can find H3. In doing so, we get H3 is equal to 157.64 kilojoules per kilogram. So now let's continue. We have the enthalpy at point 3. We also have the pressure at point 3. So at P3 and H3, again, we're going to go into table A12 and see whether this is superheated or compressed or a two-phase mixture. What we're going to find here is that our enthalpy is actually between HF and HG. As such, it is a two-phase mixture. So that makes it easy to find the temperature. T3 is just the saturation temperature at the given pressure P3. And we look that up, and that's 39.37 degrees Celsius. So that part of the problem is known. And since it is a two-phase mixture, we also have to find the quality. So let's just recall that we'll use the enthalpy data to find that quality. H3 is equal to HF plus the quality at 3 times HFG. So H3 is known, 157.64. HF is listed as 107.34 kilojoules per kilogram. The quality is our unknown. HFG is also listed. This number is 163.70 kilojoules per kilogram. And if we solve for the quality, we get the quality at the exit is 0.307, or if you prefer, 30.7%.